From the studios of Postscript Media and Canary Media.
I'm Shail Khan, and this is Catalyst.
The only reason that we don't have 10 times as much nuclear as we do today, both installed but also being built, is simply because the way that we have decided to build them is terrible.
This week, it's fission, not fusion, but that's splitting atoms.
Let's face it, environmental news is often very depressing. That's why we focus on solutions on this podcast. But still, the climate crisis looms large. Rising temperatures, mounting pollution, environmental degradation, they're all warping the planet. And for a lot of species, including us, things don't always look so great. But the story doesn't end there. Every Friday, Living Planet, a show from Deutsche Welle, takes you behind the headlines to figure out what's happening and how we'll get through it. It'll also help you make better choices for a healthy planet and find space to reconnect with the beauty and wonder of the world around us. You can find Living Planet wherever you get your podcasts.
I'm Shail Khan. I invest in revolutionary climate technologies at Energy Impact Partners. Welcome. So I usually feel like I have a pretty good bead on where the general market sentiment and momentum is with regard to any particular technology in climate tech. It's one of my great strengths, if I may be so bold. But lately, I've actually had a hard time pinpointing what's happening in the world of nuclear, specifically nuclear fission, especially in the US, and even more especially with small modular reactors. On one hand, there have been some big milestones, it appears. Among them, the first ever SMR design to be certified by the Nuclear Regulatory Commission, another one where there's a big commercial contract to deploy an SMR in Canada. On the other hand, other designs have been rejected, and there have been a series of well-informed and pretty strong critiques of the Nuclear Regulatory Commission process. Oh, and that first project from the company whose design was certified looks likely to cost a whole lot more than initial expectations, which has become a familiar story in nuclear. So it's confusing. And it's hard to tell what it means in terms of this market and whether it's really starting to hit a tipping point where we're going to see a lot more nuclear built in the US or even globally. So let's see if we can figure it out. For this one, I brought on Brett Kugelmass, who is the CEO of Last Energy, which is a small modular nuclear tech company itself. But he's also a chronicler of all things nuclear and a real student of the field. He has a whole podcast on it himself that's called Titans of Nuclear that's worth a listen. Before we get to it, I will add this. One of my favorite things about the nuclear industry is the opinions. They are prominent and they are strong. And as you will hear, Brett is definitely an emblem of that. He throws some real grenades in this conversation. I don't necessarily agree with all of them, and you'll probably hear that come through. And I suspect that given his opinions and given how this industry is structured, we'll have plenty of listeners who have their own views, some of which will diverge substantially. Those thoughts are always welcome. Listen to the end if you'd like to get in touch with us, if you can't help yourself, which I've found to be true in every nuclear conversation. But at a minimum, I hope this conversation gives you a sense of what a strongly held opinion in small modular nuclear world sounds like. Here's Brett. Brett, welcome to Catalyst.
Yeah, thanks for having me.
Let's talk about small modular nuclear reactors. So my suspicion is that most people who listen to this podcast have at least some passing familiarity with what SMRs are, but for everybody else's benefit and just to make sure we're all on the same page, can you just run through a quick definition of SMRs as you think about it, and maybe just contextualize it a little bit in the broader nuclear fission world?
Sure, yeah. I'll tell you what SMRs should be theoretically, and then the Frankenstein monstrosities that most of them have turned into as well.
Right.
So yeah, I mean, okay, so like if you look at the whole like span of nuclear technologies, you have, I mean, at some point they came up with this generation 1, 2, 3, 4 stuff, right, to help divide them up.
I've always wondered where SMRs fit into the generation number nomenclature.
Yeah, I mean, I hate to criticize that generation nomenclature because I think Todd Allen, who's one of my mentors and the department head at University of Michigan, I think he helped come up with it, but I think it has run its course and doesn't really make too much sense anymore. Now you hear a lot of people talk about traditional reactors, and maybe you could say some of them that were built 40 years ago were Gen 2s or something, and then the ones that have been built in the last 10 years are more Gen 3 pluses. But I would let's just call them traditional reactors, irrespective of when they were built. And then there's two other categories that people bandy about now, and that's SMRs, and then there's advanced reactors. And the problem still with those categorizations is that they don't really tell you that much because,
Right.
I was about to get into, the SMRs, S stands for small, M stands for modular, and most of them that are thought of as the SMRs in this generation are neither small. Some of them are bigger than the original reactors, and they're not modular. They are using traditional construction techniques that maybe have a little bitty bit of modularity built into them.
Yeah. Let's put it in megawatt terms for a minute. So small is in reference to, it's in the eye of the beholder to some extent,
I know,
right?
it's so crazy.
What do you think an SMR, what defines small to you? And then what are the sizes of some of the SMRs that are being designed right now?
Yeah, I mean, what I would think of as small is probably less than 50 megawatts. You can think about a megawatt per is 1,000 homes. So if I say 50 megawatts, you can think of, 50,000 homes in America that would power. That's what I would call small. But the industry started with small being 200 or 300 megawatts, which is only slightly smaller than the original fleet of reactors that we built out, which was 500, 600 megawatts. And now those very models have climbed up to 400, 500, 700 megawatts, and they're still calling themselves SMRs. And because some of the companies that have done that were originally affiliated with SMRs, it's just, it's hard to use the word SMR for anything that's small at this point.
And the whole premise behind SMRs as a category, as I understand it, was basically look, if you build these reactors in a mechanism such that they are rinse and repeat, they're more manufacturable than they are engineering projects. You can deploy them faster. The cost curve should be steeper, right? Instead of everything being one-off, you're going to be able to build. You're going to start to see the types of cost curves, learning curves that we've seen in all these other industries like solar and batteries and all this kind of stuff. And it approaches that sort of a world. It's hard to imagine that when you're in the 500 megawatt plus scale.
Exactly. I mean, the theory is correct. We should build small modular reactors, but we should actually build them small, and we should actually build them modular.
Right. Okay, so when we talk about small modular reactors for the next 40 minutes or whatever it's going to be, what definition do you want to use? Because what we want to talk about is what's happening in this sector. But I think that is inclusive of some of this bigger stuff, right? Even if we don't necessarily want to call it small modular anymore.
I'd say most of the real projects, the things that actually have legs, that have made their way through development or permitting or licensing or contracting, are let's say the category of SMRs, but they're not really small and they're not really modular. So I don't know what we should call them. Maybe we'll just refer to specific companies' names from this point forward instead of categories, and we can just kind of run through what's actually happening in the world.
Yeah, I think we should do that. And we should specify sizes as we're talking about it because it is a relevant metric. All right, so let's start by talking about the development of SMRs or whatever we want to call them that's actually happening in the world. I think we're going to spend most of our time today focused on the US just because it's where we are and there's some interesting activity to discuss, though I suspect you'll tell me the US is probably not where most of the action is. So let's at least start with a global perspective. Where are SMRs getting developed and built globally, and how much?
Well, there's virtually nothing actually being built globally anywhere for anything other than the traditional reactors. There's a lot of press announcements. Our company is building stuff, but we can get to that later. And then everything else is very theoretical, on paper, announcing MOUs, announcing partnerships with vendors or suppliers. But no one is, and people have maybe announced, land deals, but not even really. None of them are really contracted. I mean, almost everything in the new nuclear sector is just PR announcements with very little substance behind it.
And you're saying in the new nuclear sector, because there is nuclear getting built in the world, but you're saying it's traditional reactors. This is like, what's China building, for example?
They're always building nuclear. So at any given time, they've got 10 or 20 things literally being built underway. And I think they announced that they want to do hundreds more, and they probably will also. And then you've always got 30 projects or so. I think maybe, 50 now technically on paper, where there's literally cement being poured, equipment being installed. Vogtle, after 10, 15 years, is finally coming online in Georgia, here in the U.S. Across the world, you various states of gigawatt scale reactors coming online finally, usually after 10, 15 years of construction. I mean, that is the main problem with the nuclear industry. People can, wage all these criticisms or say that, oh, it doesn't get built because people don't like it. It's not true. The only reason that we don't have 10 times as much nuclear as we do today, both installed but also being built, is simply because the way that we have decided to build them is terrible. It's just overly complex construction, awful financial incentives. Usually the backing by governments, which the industry insists upon, ends up removing all true commercial incentives and makes these projects just drag out forever and ever and ever.
And so given that, you would think, okay, well then problem solved, SMRs. Let's build smaller stuff that is modular, right? So, but as you just said, we're not building any of that really yet. Why is that? Is it just the market is new and we're not at that stage yet? Or is that taking longer than it should be as well?
Well, let me further divide up what the market actually looks like into all of the, let's say, next generation projects. So you have, I think what we've been referring to as SMRs, and this would be the category of the GE X300 project, NuScale, Rolls-Royce. These are all traditional technology, for the most part, but at the 300 or 400 plus megawatt scale. And then you've got maybe 50 different projects that are usually smaller, though some of them are also up to a gigawatt in size, that use some sort of advanced, quote unquote, advanced technology, some different combination of fuel, chemistry, moderator, coolant, componentry. And those are your different categories. The ones that are most realistic, even by their own admission, by the way, to be built in the next 5 to 10 years, are the ones that use the traditional proven reactor technology and don't introduce some sort of physics, chemistry, or material science innovation. And then all of those others, by their own admission, probably won't come online until the mid-2030s, if ever.
And that's just a function of the state of the science and engineering of the new approaches, or is it something else?
I think it's something else. I mean, listen, their physics is great. I am sure mathematically, on paper, everything they say will work as they said. And by the way, we used to build all these variety of technologies back in the 50s and 60s. We built 50 different reactor types here in this country. I have no doubt that the reactor will work. It is the rest of the power plant that touches that reactor and the components involved in the reactor itself that when push comes to shove, when you actually build physical things in the real world, when it's not just on paper, the littlest things trip you up. And then when you surround that with the bureaucracy and the inspection of the nuclear industry, that every little thing that's off parameter settings requires years of investigations and 1,000 different people checking and looking at it to make any decision moving forward, it just kills projects. So let me give you an example. If you were to introduce even just one material science change, let's say that because of your reactor physics or your reactor chemistry, your normal 316 stainless steel or 304 stainless steel doesn't work. So you go and you work with a metallurgist or you work with another company that has some other sort of steel alloy and you get it to work. You get it to work in a lab. Great. Okay. When push comes to shove, in reality, you've now got to develop welding codes. You need insurance standards around those welding codes. You need to train up a workforce that knows how to do those welding codes. And then they have to do every weld bead across, millions of inches of welding perfectly. If there's any screw up at any point, maybe 5 years down the road, that one little millimeter that they messed up is going to cause some corrosion issue, which will cause some pressure issue, which will cause some operational malfunction, which is going to take your plant down for years. So it's like even one small change to chemistry or material science absolutely fundamentally destroys your business proposition. And the utilities are not ignorant. They know this. They've been through this before. And it's not just they're an old conservative fuddy-duddy industry. They insist we will not deploy a technology if it has any change to chemistry, material science, component industry, component innovation, period, end of story. And so that's why I say it's not the obvious reason why these next generation systems aren't going to come online. It doesn't have anything to do with their reactor physics. It has to do with the practical implementation.
Okay, so given that, and shifting entirely to North America now, I would say there's two announcements over the past few weeks that have gotten a fair amount of attention on a positive side. I think both related to, as you said, the sort of using the traditional reactor in a new design that we're calling SMRs, whether or not we decide they should ultimately be SMRs. So one announcement is GE Hitachi, the other's from NuScale. So I guess for each one, I'm going to have you just walk through like what the announcement is and what it means, and then I want to talk about what if anything these portend for, like, because I think the thing this industry is betting on is that at some point the dam breaks and you go from having 0 of these in construction or operating to a whole bunch. And at some point we end up back where we were in the 50s, where we have, 50 reactor designs, or maybe one reactor design, but we're doing 50 of them. Either way, at some point the dam's got to break because otherwise one-off project every decade is just not going to cut it. So let's talk about these two announcements and whether they provide any meaningful signal about what's coming next. So let's start with GE Hitachi. Can you just walk through that one?
I mean, you tell me. Like, I see these, and I know the NuScale one better, but I see these announcements, and I just don't see any substance to them whatsoever. And a lot of the same announcements that they recycle, like every 2 years, you'll see these headlines, and it's like new people get excited about them, and then the old people are like, wait a minute, I heard this, and like nothing. There's no substance to it. So you tell me what happened with GE, and I'll tell. Like, I know a little bit about the NuScale one, but it's like these are so insignificant from my perspective.
So the GE one is GE Hitachi signed an agreement. Now, what that agreement means, I'll admit to not knowing. But they signed an agreement to build what they call an SMR in North America. It's a commercial contract with Ontario Power Generation and 2 other companies, and it claims the project will be the first SMR deployed in North America, beating out NuScale, which we're going to talk about in just a minute.
Yeah. Okay, now I know what you're talking about. Okay, so the OPG. So they held a contest a while back, and they were going to pick from like 3 different technologies that submitted proposals, and they said they're going to move forward with them. This actually does have real substance to it. They are going to move forward. I'm sure the utility will spend tens of millions of dollars doing feasibility studies. Where it goes from there, listen, I just don't know. I don't know how you're ever going to get through the Canadian nuclear regulator. I mean, on my podcast, Titans of Nuclear, I interviewed the whole regulatory leadership there, and they're even more conservative than the U.S., and they want to work with the U.S., which I think is a disaster. Like, the only thing worse than, in terms of progress, than one regulator looking at your design is 2 looking at it at the same time. It just resorts to the lowest common denominator. They always say, instead of getting straight answers, they're always like, oh, talk to the other regulator. So I don't know. Everything in nuclear progress comes down to regulations, and I just don't see it happening. But it is good progress that they got some commercial deal in place.
Okay, and then you've alluded to regulators, which is where the NuScale announcement comes in. So the NuScale announcement is the NRC, the Nuclear Regulatory Commission, which is the regulator in the United States, much maligned by the industry, I would say, licensed the first quote-unquote SMR ever. And
Nope.
Licensed the first design? What am I? Okay, I already know I'm going to get something wrong.
Nope. No license whatsoever.
Oh, interesting.
A license is actually something you can hang your hat on. They got a certificate. Do you know what a certificate is?
I have a couple certificates. I suspect they're not the same as what you're describing. No, I don't.
No, they're the exact same as what I'm describing. So, like, you know how, like, when you, like, finish your 8th grade spelling bee contest and they give you a certificate?
This is brutal.
That's what it is versus, like, a college degree. Or, like, I mean, it's like, The certificate has absolutely no legal standing. NuScale's done a great job.
Wait, can you
Listen,
describe what it is? Like, what did
it's
NuScale get?
nothing. Zero.
This is the first of this kind of nothing, right?
Yes.
Okay. And is it a precursor to something?
Sure. Yeah.
Okay. So
is your 8th grade spelling bee certificate. Yeah. It's a precursor to no, but I'm not actually kidding here. Like, they have not even started a license application. The license application is going to go on for 5 to 10 years. They'll promise 4, and it'll go on for 5 to 10 years, and it'll cost them between $500 million and $1 billion before they get to start building anything. And they haven't even started that yet. The certificate is worth nothing.
Is it a core part of the... Actually, maybe this is a better way to ask this question. Walk me through the NRC process as it exists today. Say you're NuScale. Say you're somebody who's developing an SMR reactor, a new SMR reactor, a new system. What is a process that you have to go through? And then I guess in that context, we can say, like, where does this milestone fall along the process?
Yeah. So if you want to build something, you can go between... there's 2 different schemes that you can go in front of the NRC for, the Part 50 or the Part 52. And these are just 2 different licensing paradigms that have been set up over the last few decades. And in order to get a license, you have to submit a license application. It is at minimum, in the US, it's at minimum 4 years worth of work. No one has done it for less than $1 billion. No one has spent less than $1 billion in licensing fees and gotten one of these. And actually, no one in the entire history of the NRC has gone through the whole process from start to finish and turned on a reactor. In 48 years, not a single entity has gone through this process.
Can I just jump in for 1 sec? What is Vogtle?
Vogtle is not turned on yet. When Vogtle gets turned on, it'll be the first in all of human history to have gone start to finish through the NRC licensing process. Every single other nuclear installation in this country was grandfathered in from the Atomic Energy Commission, the predecessor agency to the NRC. So, yeah, Part 50, Part 52, license. So several companies have gone through it and spent $1 billion, including Westinghouse, GE, EDF, a few others. They spent $1 billion and they never actually built anything because it took too long and the projects just became too expensive by that point. But Vogtle will be the first.
And so then, as you're going through that process, what is certification of a design? Where is that in the process?
Certification is like we said, it's a certificate. It's like a piece of paper that says, congratulations, you're proficient. We've looked at your work and we think it's great. And it makes everyone feel happy and gives investors confidence. But you're still at least $500 million and 4 to 10 years away from actually getting a license, which allows you to build and turn on a reactor.
And do you attach any significance to the fact that this was the first SMR design to get certified?
It's not small. It's not modular.
You just don't want to call it an SMR, so you think it's...
No, I listen, I think it's great that they're doing it. I think they're, pushing through legal malaise and regulatory malaise. I think that's always a good thing. I think they're bringing a lot of excitement and interest into the space. They are bringing forth innovations for sure. So I think this is all good. It's just not the hard part is getting a license, and they haven't even started that yet.
And as you say, it's not small and it's not modular. Maybe help me dig into that a little bit. As I understand it, NuScale's reactor is like a 50 megawatt reactor.
Not anymore. That's the other thing maybe we forgot to bring up. The things that they got the certificate for are deprecated designs. So no, they don't have everything that you're seeing is for something they submitted years and years and years ago, and they've totally thrown in the trash at this point also. So no, it's for a 50 megawatt reactor. They're not building a 50 megawatt reactor. They have no intention of ever doing that. They've shifted up to a 77 megawatt reactor. And they got to go through this whole process again, even just to get a certificate, which still has no weight.
So they're going to have to recertify this new reactor, basically.
Or they just go straight to a license. Once again, the certificate thing has no legal merit. It's just a way to spend time with the regulator to get them comfortable and familiar with your technology. Like I said, I still think it's a good thing that they're doing it, but it doesn't show the progress as they're trying to advertise. That's more of a marketing hiccup on their end, or maybe not even a hiccup, a good marketing strategy on their end. But if you talk to any of their technical folks, their engineers, none of them will tell you what you're seeing online.
The NRC process is also an area where there's been news and, I don't know, opinions and all this kind of stuff. I'm sure you have your own. Can you walk through, at some point, Congress or the president said to the NRC, we need you to overhaul your process because, for exactly the reason you described, nobody's ever gone through it end to end. It costs $1 billion, and we need nuclear. So what was that directive? And then what has the NRC done in response?
Yeah, so this is a weird thing because most of these types of agencies sit in the executive branch. When the NRC was created in 1975, it was actually set up as an independent agency, so the president can't really tell them to do anything. So it has to be Congress. Congress passed a law saying they had to clean up their act because, once again, and by the way, as I say all this, I just want to say, I'm not criticizing the people at the NRC. The people are smart and great, and I've spoken to a lot of them, and I think they're, and they mean well. All my criticisms are against the institution itself. And a lot of these same critiques could be held against many government institutions, not just the NRC uniquely, but we'll focus on the NRC here. Congress set them up, independent agency. President can't tell them what to do. Congress has to tell them what to do. Congress told them to expedite it, and they didn't. Instead, they wanted them to streamline it, especially for these newer reactor designs. And they took all of the old regulations, the regulations that drive up the costs to $10 billion or to $1 billion, make it take 10 years, and then they added 1,200 pages of new regulations.
And do you have a sense of how and why that happened? I mean, again, to your point,
it's an institutional problem. It's not a people problem. It is an institutional problem. The institution.
Can you just say more? What does that mean?
So it was set up as a single mandate organization, not a dual mandate organization. So a dual mandate organization is like the FDA. We know penicillin kills some people, but we're able to look at the cost-benefit analysis and say antibiotics are better than they are worse. And so you're allowed to commercialize penicillin and other antibiotics, and they're allowed to consider that. The NRC, the way it's set up, was a single mandate organization. Safety, not considering any other externalities. So if there isn't even the remote chance that one person might get injured in 1 million years, they are legally not allowed to push a design forth. Like, they can only say no. Institutionally, that's how it's set up.
So what you're saying is that in order for things to really change, Congress telling the NRC to expedite won't matter if the NRC remains by design entirely focused on safety with no other considerations. So what would have to change is the institution of the NRC. Congress would have to say, actually, we're gonna change the mandate of the NRC.
I think you'd have to overhaul so much more because there's like other cultural issues too. I mean, there's another thing, so there's like rulemakings and everything that have built up over time. And so you'd have to pick apart all those too. Like any single person, you could be an administrative assistant at the NRC at any point can raise a safety flag on any project and shut that project down for 2 years. This could be someone with no technical training whatsoever. If they come across a piece of paper on anyone's desk anywhere in the NRC and they say, this doesn't look safe to me. Remember, no technical training whatsoever. That can set off a 2-year investigation that could cost a company hundreds of millions of dollars, delay projects. Like, that is written into the institution itself. So yeah, you need a serious overhaul or a branching or splitting off or a new agency being created. There are a lot of ways you could do this, but it's going to have to be drastic.
Okay, so given all of that, let's step back. It seems like what you're saying is that the recent sort of small raft of announcements that we've seen, maybe there's some others that you think are important that I haven't alluded to besides this Hitachi commercial agreement and the NuScale design certification. It sounds like you're saying we shouldn't take a whole lot from those. Like, it's not a signal of the momentum suddenly building where it wasn't before, or the dam breaking, whatever metaphor you want to use.
I think the momentum is building for many reasons. But yeah, I wouldn't take those particular announcements as a signal.
Okay, so how is the momentum building?
So social and political support for nuclear has never been stronger. It is coming out of the woodworks, like from all different angles. People who have never even spoken to anyone from the nuclear industry, like, are putting their like political and like careers on the line in support for nuclear. I think it's probably a combination of social forces, but most of this hit a tipping point about 2 years ago, where all of a sudden it became like part of the zeitgeist. It became in vogue to say you were in support of nuclear. I think a lot of this has to do a lot more with energy security, and then even potential like climate concerns as well, where people are just not seeing the progress that they were promised across other technologies, and they're seeing many of the downsides, and are all of a sudden like naturally, like revisiting, with their the previous notions, their misconceptions around nuclear, and just giving it a tabula rasa, like, okay, ready to go. Why don't we re-explore this? And then once you hear like one or two people in your ecosystem say it, a few forward like thinking, leaning people that you affiliate with, maybe on a few other topics as well, it becomes more like okay for you to then say it in the public sphere, and then this builds and builds and builds upon itself. And yeah, it hit a tipping point a couple years ago. So now you can go almost anywhere in the world, and most places even in this country, and say, hey, I think we should build more nuclear, and people say, I agree, let's do it. Why aren't we doing it?
So I agree with you anecdotally on that. I do think that the public sentiment seems to have turned. I guess the question is, what does that manifest in? Like, what does that need to turn into in order to shift from like, now we all publicly agree that we need to build more nuclear, but we still have this intractable problem of getting reactors certified and built?
Oh, we don't have that problem. We have that problem in the U.S. Globally, we do not have that problem. Like with
No, I mean in the U.S.
Well, yeah. Well, I don't know. I think it's probably an intractable problem here.
Interesting. Okay, so your outlook is just like fundamentally bearish on nuclear in the U.S. specifically, and bullish in the rest of the world.
Yeah, though once again, I do think once it's proven out in the rest of the world, I think things will drastically change here, just because we'll have proof points and examples abroad, and we're going to look like idiots. And like there's a lot of pride that we have as Americans about being the first and being the best, and I think that can definitely overwhelm some like institutional inertia that needs to be overcome.
Where do you look at as like the bastion of the next gen nuclear in the world?
I think the most activity that we've seen anywhere, like once again, including with our own company, is in Poland. There's like a confluence of circumstances there between, sustained political and social support. Their energy security issues, bordering Ukraine, are ever present. The fact that it's mostly coal, but yet still part of the EU, and so they're being like penalized for having so much coal. But they also want to shift off coal too. The fact that it is an incredibly productive and growing and industrializing country. I think Poland will probably lead the way in terms of, and they've got like 4 major projects underway. Westinghouse building gigawatts of reactors out there. NuScale paired up with KGHM, the copper company. GE paired up with Synthos, the chemical company. And then my company, Last Energy. I mean, we've announced almost 20 deals out there now that we've signed and are starting development activities on.
Let's talk about cost for a minute. This is one of these areas like, so the cost of nuclear power as delivered is all over the place from what I can tell, right? Like totally. There are places where you're like, oh, nuclear is like super cheap energy. And then there's other places and situations where nuclear turns out to be quite expensive energy. Oftentimes you hear folks point to the regulatory process as a big part of the reason for that, both the literal cost of getting certification for a reactor, but also the cost that the regulatory process imposes on the system itself and the engineering cost and so on. Is that your view as well, that like the fundamental driver of high cost nuclear is regulatory, or do you think that it is a function of the reactor designs and the systems themselves?
Both. So I would say the proximate cause is regulatory, but the root cause are market incentives driven by the industry, the nuclear industry itself, to self-impose those costs, mostly in a rent-seeking behavior and acting through regulatory capture. I can break that down if you'd like.
I would like.
Yeah, so we go back in history. These plants used to be like as cheap as you could imagine. And by the way, like these are plants that are still operating today. Like, okay, so my favorite example is Point Beach 1 and 2. They were each about 550 megawatts. So now you have an 1,100 megawatt, a gigawatt system broken down by two plants that in 2020 dollars was $733 million. That's less than $1,000 a kilowatt. That is your cap. And we already know that the nuclear OpEx is already cheaper because your fuel as like a percentage of energy is like negligible. And then now you also have the CapEx being like the cheapest in the world. So here we have like real, and those plants are in Wisconsin are still operating today. So here we have like real living proof. Oh, and they were first of a kind, right? So it's like no real experience. No real experience. They built two plants. They were some of the best ever, built in 3 years. We could just build those, by the way. If we just like went into those facilities, like looked at the blueprints and the schematics, built them exactly how they were built, we would decarbonize the entire planet and every human being would have energy that's like 5 times cheaper than they're paying today. And that is with 1968 technology that is still operating today.
What does that like roughly translate to in terms of cost per kilowatt hour, in terms of LCOE?
Well, it depends. And this is where some of that regulatory capture, rent-seeking behavior has driven up the operational costs far beyond where they need to be. But if you just built those and also had like 1960s operating costs, you're talking like $15 a megawatt hour, or like 1.5 cents a kilowatt hour.
Right. Okay. Super cheap.
I mean, you can't get better than that. Yeah.
Okay. So you're saying there's precedent historically for very, very cheap nuclear that works for a long time.
Yep.
And this is, I guess, one of the things I don't really understand, though. I don't see any of the new designs even targeting $1,000 a kilowatt, right? And so why?
Yeah, because new chemistry, new material science, new physics is extremely expensive.
Okay, so why can't we build more of the old stuff at that price?
We should. We absolutely should. We should build 10,000 Point Beach 1s and 2s.
But we're not because, and even forget the U.S. regulatory stuff, right? Say globally.
The industry incumbents, starting in 1968 and working all the way up to 1978, because of the way that the market was set up, they weren't allowed to get paid based on cheap and efficient power plant design. They actually got reimbursed more if they would build it slow and expensive, because the way the market was set up on this cost-plus model. And so that went on in this country till the 90s. But what you saw from 1968 to 1978 was a tenfold increase in price for the exact same product delivered, because that was a tenfold increase in the profit that the companies were allowed to make if the public utility commissions essentially lock you in at a fixed profit, like let's say like 5% or 10% of whatever you build. So that is how market incentives and market design influenced the behavior of the incumbents. And then it got out of control by 1978. By the way, this is the year before 3 Mile Island. 200 contracts were canceled. So the nuclear industry was absolutely destroyed. And then the industry actually transformed from companies that build power plants to companies that sell safety systems to existing power plants, cannibalizing their economics in that rent-seeking behavior. And so all you have now, all the incumbents, the people with the IP, or the people theoretically with the IP or the knowledge to build these plants, don't want to build plants cheap because that's not what they were trained to do. And most of them are dead anyway, the people who actually had any experience building plants. So we killed an industry through market design, and then the industry has been stagnated for 40 years. And so even though we have living proof of like the perfect design in front of us, we can't get out of our own way.
All right, so what's going to happen? Like, paint me, most likely next 5-10 years in nuclear development.
Yeah. So I'll tell you what we're doing, and then I just hope a bunch of people will copy us, and then it'll just accelerate how this all plays out. But what we're doing is we're taking that standard design, no new innovation on components, no new change to material science, physics, chemistry. Like, we learned our lessons from like industry professionals who know about operating power plants. And then we just shrunk it down as small as we could so we could build it actually modularly, build it in a factory setting. There'll still be cost overruns on the first few units, but because we've reduced the CapEx to under $100 million, those are like tolerable overruns. And then as you get better and build more, the costs come down and down. And then you get into a habit of building thousands of really small, in our case, 20 megawatt power plants. And then you get to increase the power. After you've proven yourself, after you've built 100 20 megawatt power plants, you can build 100 200 megawatt power plants, and then maybe even 100 2 gigawatt power plants. And so this is like our defibrillator to the industry. This is our plan to resuscitate an industry that is, hanging on for dear life and get everything back on the right track.
Okay, so final question for you. We've been talking about traditional reactors. We've been talking about quote-unquote small modular reactors, all of those still in the tens of megawatts at least scale. There is another category that I'd say is probably even earlier stage, which I guess some people call microreactors, which is nuclear reactors that are very small and maybe better suited for off-grid applications, defense applications. Some of them are sort of planning on behind the meter applications on the grid in the long term. Where do those sit in this whole universe? And is there any reason to think that their regulatory pathway would be any cheaper or any different from the rest?
Yeah, so that's what we're calling ourselves now, because the term SMR was just so bastardized by these large, not modular projects. We have decided to adopt the other terminology, microreactors, which you brought up. Most other microreactors use some sort of new chemistry, fuel, material science, a fundamentally new reactor, and then can go even much, much smaller, maybe down to 1 megawatt. But some are up to 10 or 20. 20 is our size. And yes, many of those applications I think are great. And I think it's a great way to break into the market too, whether it's remote or defense, because the energy costs that are higher, you can sell your power for higher, which means that even though you're smaller and might not have the same economies of scale of size, that's okay. You can still keep a pretty good profit margin. So I think, microreactors are a great path to go. And then, our differentiator is simply that we're the only microreactor company using proven technology.
All right, Brett, lots to talk about in nuclear world. You have a whole podcast on it, so obviously you found plenty to talk about. But this was fun. Thank you so much for doing it.
Yeah, no, thank you for having me. Glad to shed some light on what's happening around the world.
Brett Kugelmast is the CEO of Last Energy. As always, send us your questions, or in this case, your missives about nuclear, or tell us what else we should cover on this show. You can leave us a voicemail. The number is 919-808-5832. That's 919-808-5832. Or you can email us at catalyst@postscriptaudio.com. You could also tag us on Twitter. If you like the show today, go over to Spotify or Apple Podcasts and leave us a rating and review. This show is a co-production of Postscript Media and Canary Media. You can head over to canarymedia.com for links to today's topics. And as always, Postscript is supported by Prelude Ventures, the venture capital firm that partners with entrepreneurs to address climate change across a range of sectors, including advanced energy, food and agriculture, transportation and logistics, advanced materials and manufacturing, and advanced computing. This episode was produced by Dalvin Abouaji and Daniel Waldorf, mixing by Roy Campanella and Sean Marquand, theme song by Sean Marquand. I'm Shail Khan, and this is Catalyst.